Hello and welcome back to the Sports Biomechanics lecture series. As always, supported by the International Society of Biomechanics in Sports and sponsored by Vicon. I'm Stuart McCurlane-Naylor from the University of Suffolk, and today I'm joined by Tony Myers, who is a Professor of Quantitative Methods at Newman University, and he's also Chair of the Sport, Exercise and Health Analytics Special Interest Group for the British Association of Sport and Exercise Sciences. And Tony has kindly offered to record a lecture on Bayesian statistics for sports sciences. And this is a topic that a few people requested after Kristen Sanani's excellent lecture on statistics a few weeks back now. So I was really happy that Tony agreed to deliver that. The lecture is pre-recorded, so if anybody has any questions as we're going along, either drop them in the comments on YouTube or get in touch with either myself or Tony via Twitter, for example. And one of those ways we'll try and make sure we get an answer to you. Thank you.
Thank you, Stuart. My name's Tony Myers, and this presentation is on Bayesian data analysis. The aims of the presentation are to very briefly highlight some of the issues identified in traditional approaches that we've tended to use in sports science, and particularly pointing you to sources where you might explore these issues and solutions further. Look at one of the solutions to the issues highlighted and look at the benefits of Bayesian data analysis, provide an introduction to some of the basic concepts of Bayesian data analysis, look at perform and interpret some very basic analysis using some very user-friendly software, JASP, that's free to download and constantly being updated. And then show an example of Bayesian analysis workflow that involves a little bit more complex analysis and slightly different software, just to highlight some of the things that you might want to explore further. There's been a number of issues identified with traditional statistical approaches. Of particular importance was a follow-up to the American Statistical Association statement in 2016 about caution with the use of p-values. And this particular special edition of the American Statistician in 2019 went beyond their previous claims. And this was an editorial in that special edition called Moving to a World Beyond P is Less Than 0.05. What did they say? What did they add to their their previous 2016 statement? Well, basically what they said was it's time to stop using the term statistically significant entirely, along with variants such as significantly different, p is less than 0.05, non-significant, or other forms where you might highlight these things by asterisks in a table or in some other way. So what are the alternatives? If we take their suggestion seriously, what are the alternatives? Well, there are a number highlighted actually in that particular special issue, and it's worth looking at those, including the proper use of traditional p-values. So there are a number of credible alternatives, and one of them is the focus of this lecture, and it's Bayesian data analysis. What are the benefits of Bayesian data analysis? Well, one is the use of prior scientific knowledge. This is potentially also a double-edged sword, because how do we agree what prior scientific knowledge is? But certainly it's a way of incorporating what we already know about something, even if it's, and we do often know about something, even if it's only about the measurement itself, about what the measurement scale is in the problem that we're addressing. We produce, with Bayesian analysis, distributions and uncertainty estimations in a distribution rather than in an interval. And this has benefits for its communication. It has benefits for particular calculations of probability, which are very intuitively interpreted. So probability in the intervals generated are sort of like common sense interpretations of probability. When we talk about a 50-50 chance of raining, we give a chance of raining 50%, and that's how we generally talk about in everyday language probability. And Bayesian probability allows us to use those type of probability statements. It doesn't rely on hypothetical data for inference. So where we, in a traditional analysis, match our data, to look at the compatibility of our data with a hypothetical null distribution, it doesn't do that. Bayesian analysis allows for model comparison. I know traditional analysis does, but we've got a number of tools to compare models, to both criticise and explore those models in a very straightforward way. And complex models that are problematic for non-Bayesian analysis methods can be constructed. So these are some of the benefits. Like any other type of analysis or any other type of endeavour, garbage in, garbage out. If your method's poor and your research is ill-conceived, the best statistical analysis will not rescue the study and make your results useful. We use a sample to draw conclusions about a population, and we do that either by estimation or hypothesis testing. We either estimate differences, relationships, variation, or test a hypothesis comparing either null to a research hypothesis or compare hypotheses. We tend to make inferences about groups or actually individuals potentially. So we sample from a population of either measurements, so it doesn't actually have to be just people, it can be measurements over time of an individual. We're making inferences about that population from the sample. And it's important to be clear what population we're attempting to generalise to. Subgroup, geographic representations, etc. Why? Well, particularly in Bayesian analysis where we're incorporating current knowledge, we're using prior knowledge before we collect the data. And that prior knowledge will differ depending on the population we're trying to describe. So the basic principle behind Bayesian inference is to start with prior knowledge and combine that with data in the form of a likelihood, and that produces a posterior distribution. So how is Bayesian hypothesis testing different? Well, first of all, it uses a Bayes factor rather than a p-value. And we've got a Bayes factor 1, 0, which tells us how likely the observed data are to occur under H1 compared to H0. So in favour of the alternative hypothesis or our research hypothesis compared to the null hypothesis. For example, how likely there is a difference compared to how likely there is no difference following our intervention. Bayes factor 0, 1 is the reverse. It's how likely the observed data are to occur under H0 compared to H1. So how likely is the no effect compared to an effect, for example. So Bayes factor 1, 0, we've got a scale. 1 means equally likely either way. Evidence doesn't favour either the null or the alternative hypothesis. As we go from 1 to 3, evidence starts to get stronger, but really between 1 and 3, it's still anecdotal. It's really, we don't want to make claims for an effect. When we go above 3, we start getting what we might call moderate evidence, above 10 strong evidence, above 30 very strong evidence, and above 100 extreme evidence favouring our research hypothesis or the alternative hypothesis. And Bayes factor 1, 0 is the same but in reverse. So where we've got 1, it's the same thing. There's no difference between evidence favouring the null or the research hypothesis. But as we go to 3, it starts favouring the null a little bit, but we can't make any claims. Then we've got 3 to 10 moderate evidence, above 10 strong evidence, above 30 very strong, and then above 100 extreme. So it's just the reverse of Bayes factor 1, 0. Which you choose depends on what research question you're interested in. So let's take a look at a silly example just to look at how we interpret Bayes factor 1, 0 in relation to a hypothesis. We're looking at whether the person's pregnant or not, and the BF10 suggests that we have extreme evidence for the research hypothesis of pregnancy. You can see the little maroon graphic, the pie chart, which is something produced by the JASP software and can illustrate that. So all maroon means most complete support for the research hypothesis. Take our next example. Presuming we have no prior information about sex differences in pregnancy. In this case, we're not sure. We have one which is in between. It's a 50-50 chance in the pie chart. Maroon and white are evenly distributed, half and half. So we're really unsure about whether this person's pregnant or not. Final case is the evidence suggests that the person in the picture is not pregnant. And we have extreme evidence for that with a Bayes factor 10 of 0.003, almost zero. So that's how it works. So we evaluate strength of evidence given Bayes factor. So it gives us perhaps a little bit more than a p-value. So does Bayesian parameter estimation differ from traditional parameter estimation? Well, firstly, rather than just point estimates, we get a distribution, a probability distribution of any parameter that we're interested in. So mean differences between treatment and control, mean difference in pre and post, relationship values, whatever we're interested in, whatever parameter we're interested in, we get a distribution on that parameter that represents our degree of knowledge and the uncertainty around it. So this is what we get when we've conducted a Bayesian data analysis. This is the posterior distribution. So it's a Bayesian posterior probability distribution. And this particular example is differences in sprint times between a control and treatment group. So we've got a range of potential differences here from minus 2.5 to probably almost 6 seconds difference between those two groups. And we've got density on the left. So what does this mean? Well, the higher the density of Y, the more probable that X value is. So in this case, something like 2.45 seconds is likely to be the most probable difference, conditional on the data that we had. So the most likely probable population estimate we have is likely to be 2.45 seconds in terms of the differences between the control and treatment group. The lower the density of Y, the less probable that X value is. So this is much lower. So 0 is much less likely because the density at Y is much lower than the midpoint of that distribution which you just looked at. With the Bayesian credible interval, with this posterior distribution, we can say there's a 99% chance the true population difference is contained in this interval. This particular case, minus 0.09 and 4.56 seconds. Now, of course, all of these percentages are completely arbitrary values. We've got traditional sort of value of 99 and 95 we use for traditional statistics, but they are purely arbitrary values. We could calculate 95%, a 95% chance the true difference lies in this interval, so between 0.27 and 4.19 seconds. Calculate a 90% chance, an 80% chance, and these arbitrary values, depending on what we want to calculate, is very straightforward and easy to do. Another property is that's very useful is we can get the probability of a difference above any particular value we want. So if we've got an idea of measurement error or of above a particular time difference would be really important in the context we're looking at, we can very straightforwardly calculate a probability of a difference above a particular value. What this allows us to say, which we can't say with traditional statistics, if we have an effect, for example, we could say there's a 90% chance that this intervention will be effective increasing in strength, or there's a 98% chance this intervention will be effective increasing in speed, depending on what we're looking at and obviously depending on the size of the effect. But we've got direct probability statements about the effect, and that's different. We're not comparing it to the null. We obviously can balance the null and the research hypothesis evidence for both with Bayes factors, but when we're trying to make parameter estimations, we generally can get direct probability statements either way. Of course, it could be 50-50 either way, it could be any percentage we find, but we can say that and communicate that in a language that people tend to understand. probabilities that make sense in a practical way to practitioners, coaches, and even researchers. Now for the symmetrical posterior distribution we just looked at, the two types of interval, the two types of credible interval I'm going to talk about now, would be exactly the same. So have exactly the same values calculated in any of the intervals credible intervals that we calculated. However, that's not the case for skewed distributions, as we'll have a look at in a moment. So the two types that a credible interval are generally calculated and reported are the highest density interval, or HDI, sometimes called highest density posterior interval or highest posterior interval, and this captures in the HDI all points within the interval have a higher probability density than points outside of the interval. And that can be important, particularly when we're looking at skewed distributions, because we will get differences. The other type of interval is probably familiar, you're perhaps more familiar with really in terms of a traditional confidence interval, the way it's described at least. So this is an equal-tailed interval, so depending on what sort of percentage you talk about. So if we're talking about a 95% equal-tailed interval or ETI, there's 2.5% of the distribution on either side of its limits. Let's take a look at what that looks like and how they differ when we've got a skewed distribution. So this is the 95% higher density interval of the difference in sprint times if it was a skewed distribution. If we compare that with an equal-tailed interval, we see that the values in that interval differ. And in this case, because it's in the values that were measured, so the non-transformed values, the HDI, the 95% HDI is the best units to use. In transformed variables, ETI will be the best bet. But generally, higher density interval is the best bet when we're using the units that we've measured. So, Bayesian analysis allows us to determine probabilities associated with both the null and the research hypothesis. And that's something we can't do with traditional hypothesis testing because we assume the null's true. So all the probabilities are based on assuming the null's true in the first place. Importantly, when we're doing parameter estimation, we get intuitively interpreted credible intervals. Let's look at some basic data analysis using JASP software. So I really do want to big up this software. It's not only free to download and use, but it's constantly being updated. Okay, let's have a look at the data first. Now this is simulated data. It is based loosely on a study that was conducted, but is the data that was just loosely based on that in terms of me simulating some values. So the actual study involved participants being blinded from each condition and the amount of capsules, caffeine capsules, received were the same irrespective of the dose. So they got either placebo or 3 milligrams per kilo of body weight of caffeine. And the dependent variable in this particular instance is 3 counter movement jumps. This is the data. This is what the data looks like, spreadsheet. It's the JASP software, so we're going to look at JASP. Certainly I'm going to look at this software. As I say, there's a range of traditional and Bayesian tests, and you've got equivalence testing, you've got mixed effects models. There's a range of things you can do with it now, and it's constantly being updated, and a great supportive network for the software. So I can't recommend it highly enough, really. It's really excellent. So we enter the data into the JASP package using a CSV file. So I'll save the Excel sheet as a CSV file. It's one of the options in Excel, and it looks very similar to the spreadsheet. Now I'll go on to the menu, t-test menu, and select Bayesian paired samples t-test. I'm very similar to you might do in SPSS or some other similar type of software. I'll click on the variables and transfer them over to the analysis window, and I get some output in the right hand pane, if you like. I'm going to add prior and posterior information visually because I think that's useful, and I can also click some additional descriptives to have a look at what's happening. So it looks like in the descriptive certainly the caffeine had an effect, a bit more variation in it, and higher standard error. What does that come out as when we look at the graph? So we've got the dotted line gives us the prior. In this case, it's a Cauchy prior centered on 0 and a 0.7 approximately scale. So we've got a fairly broad prior, but it is centered on 0. And given that prior, we get this particular posterior there. So that's a posterior distribution with a continuous line rather than the broken line. And the Bayes factor tells us that the data are 8 times more likely under the research hypothesis than under the null. If we wish to summarise about the differences, and this is in terms of a standardised effect size. So the effect size is similar to a Cohen's d effect rather than raw values. So we can summarise and say that the differences in conditions, there's a 0.6 of a standard deviation difference. So if you do like, I'm not a fan of it, but if you do like the sort of standardised, the sort of categories for effect size, that would be a medium effect. We can also get that's reflected in the middle of that posterior distribution, the median value of the posterior distribution. That's why it's called median. And then we get the 95% credible interval, which tells us there's a 95% chance that the true difference lies between 0.164 and 1.120. Look at what that looks like visually. I really would suggest that website's really excellent. It also provides a range of other simulations, but you can actually move the scale on this and have a look at what different Cohen's D's look like, what different standardized differences look like. And this particular point, I've just moved the scale to 0.63. And what this suggests is, I think also it gives some other interpretations. One useful one is the Cohen's U3, which tells us that actually this size of difference in terms of standard deviations means that 74% of the caffeine condition are above the mean of the control condition. So it gives us a sort of common sense interpretation of that particular standardized difference. If we were to run a standard pair samples t-test on this, we'd see that we've got a p-value that would suggest that the data isn't really that compatible with the null. So we'd say the data would be surprising, I guess, if there really was no difference between these groups. So in that way, a similar conclusion in essence. And we've got values of our confidence interval. Those are different because they're not standardized differences. Those are in raw differences. So we've got a moderate effect in terms of our Bayes factor. Now we can do some additional stuff which I think is really useful to have a look at the effect of different widths of priors. So if we have a look at the Bayes factor robustness check, all the priors, even a very wide prior, comes up still in this moderate category. Another interesting analysis we can do, or check we can do, is the sequential analysis. So this tells us how evidence shifts with each data point. So we can see initially there was some evidence for the null hypothesis, but then as more data was collected, evidence became stronger for the alternative hypothesis, for the research hypothesis. So let's take things further and conduct some additional Bayesian data analysis with some different software. We'll mention, while I'm here, all these different softwares that I use and I think are really excellent. So JASP we've mentioned, but also Stan. I use an interface with R, but you can use it with Python, and INLA, integrated nested Laplace approximation, which is really quick. I tend to use, but not always, but often use the BRMS package in conjunction with Stan because it's really flexible and helps you produce models quite quickly. So let's have a look at the efficacy of a post-game recovery protocol. Now, this is simulated data, but it's not completely made up. I've tried to use some values that I've previously got from studies I've done in the past. So, groups involved, treatment and control group, randomized. That's not actually always possible in applied context, but for the simulation, it's no problem. Measurement, baseline, 2 hours post-game, and then 24 hours post-game. Dependent variable, 30 meter sprint speed. So this is data that's been simulated, but is not, is similar to some data that's actually been gathered, some actual empirical data. So let's have a look at the efficacy of the post-game recovery protocol, in this case for basketball players. Workflow in this sense, I'm going to explore the data visually, fit different plausible models based on my visual exploration of the data, do some diagnostic checks, compare models using two different systems, one Bayes factor, the other one leave one out cross-validation. Then I'm going to look at how you might extract some key information to address the research question. Exploring the data visually. So simply make some box plots of the three measurement points and the two groups. So we can see here the baseline, the pre-measurement, the baseline measure. Treatment group slightly faster, slightly higher sprint speed, meters per second. Both groups drop off in the post-measurement, unsurprisingly, post-game, and then both recover a little bit. It looks like, visually, that it may be the case that the treatment group seems to be doing better, but we actually have to look at what the outcome is of the analysis. Also want to plot, just to have a look at the density of the sprint speed, the Y variable, the dependent variable. In building the model, I'm going to use a response distribution. Now, I will use different response distributions, like a Gaussian distribution, maybe a T distribution, but I'm going to use a skewed normal distribution given this particular information and see whether it actually proves to model the data better than the other distributions. One of the advantages of Bayesian modeling is that I can do this very flexibly. So, like in all data analysis, there are a number of subjective decisions need to be made. What I'm going to do in this as an overall model, even though I'm going to change things like the response distribution and different prior information, what I am going to use is, given I've got baseline measures for both groups, I'm going to compare post measures at the 2 hours and 24-hour measurement points using baseline as a covariate. So it's post measures conditional on baseline, condition on baseline, so I'm adjusted for baseline. So this is similar to an ANCOVA model and helps potentially avoid regression to the mean, particularly given all that kind of affected, all the treatment kind of affected is the post measures. It kind of affected the baseline measures. So the ANCOVA model seems to me to be an appropriate model. I'm going to use different priors. So I'm going to use a weakly informative prior, and this is a mean of 0 and a standard deviation of 3. So it gives me a broad range of differences. They're actually very unlikely. So it's unlikely I'm going to get minus 10 meters per second difference in a 30-meter sprint between the groups, or plus 10 meters per second. So this is really weakly informed. It's not a uniform prior, so it's not putting probability across all values, but it's still very broad. As far as the prior for the intercept and the standard deviation go, I'm going to use the BRMS prior. So I'm going to use the BRMS package to fit this model, and I'm using these as prior. So it's a T distribution on the intercept. So it's allowing, with the long tails, allowing values that are quite broad. I found it useful in a number of models, so I'm going to stick to the default model. Very similarly to the standard deviation, which is a half student T. Doesn't allow me to have minus standard deviation, so it seems it's a reasonable choice and has worked well as a default. Measurement constrained prior, what this is, what I'm trying to get at here is, I've tried to think about what really, given this is a group that's been randomized to control and treatment, what likely differences are there going to be in sprint times? And I don't think they're going to be that much more than, say, 2.5 meters per second either way. So I've centered this as a mean of 0 and a standard deviation of 1 to try and capture that. Again, I'm going with the defaults on the intercept and the standard deviation. My informative prior, really based on some previous data, so there's some previous studies that have looked at a similar thing. and knowing which way round my groups are in the regression model, then I'm going to put a mean of minus 0.5 and a standard deviation of 1 to reflect the sort of general differences that have been found on average in some of the previous studies. Again, I'm going to use the default priors on the intercept and standard deviation. So, got these weakly informative prior, differences modelled by a normal distribution, the intercept standard deviation by the defaults in the package, measurement constrained model, and the informative prior based on previous studies. So these I'm going to include in all the models. So I'm going to check, so I'm going to do lots of different models in essence. I'm also going to model this on a normal response distribution. So as a normal response distribution, a skew normal, given that the shape of the y variable when I looked at the density of it. I'm going to allow individual intercepts to vary because it looked like there's actually quite different sprint speeds across both groups. And I've got several data points for each person. And I'm given, again, it looked like there were differences in variance across the groups. I'm going to allow for heteroscedasticity in the group. So again, I can build that into a model quite straightforwardly in the BRMS model or in STAN. Run the model. So this is some of the plots for the best model in the end. So I've got some trace plots, see whether they visually there's any problems. Even though just a visual inspection won't necessarily identify problems, I can see if there is a problem. I won't be able to say just because it doesn't look like there is that there isn't. So I also do want to do some other checks. The R hat, which comes out of the as an output in STAN, and the BRMS package, and some other packages as well, allows me to say, well, if I'm looking for an R of around 1.01, but anyway, certainly less than 1.1, and it appears that they have all converged as much as we can tell at least. So it's likely that's past that diagnostic check. I'll point out the leave one out cross-validation package, but this allows me to produce this plot and have a look at whether any influential values, potentially outliers, but they're influential values that might cause problems, that might be problematic for the in terms of the estimates. Potentially 35, data point 35 is, and possibly 3 and 11, but I'm going to leave those in. But I certainly could remove them if this was a real analysis. Then I look at posterior predictive checks. So I'm looking at whether the simulations in the model actually match the data. So I'll look at, is it a real reasonable match for the dependent variable, the y variable? And it sort of looks like it is. So those lines, those lots and lots of lines, are 100 simulations from the posterior distribution, and the black line is y. So y versus y rep. And the empirical cumulative distribution function as well, in the same way, it looks like it's captured it. And then I can go down to the means and standard deviations of the groups on the bottom plots, and it looks like the simulations seem to have captured the descriptives in the data. So I'm pretty happy that's captured the data well. The data, obviously, I know. The rest of it's random variables, but I do know the data. The data are fixed in a Bayesian model, and I know what that is. So I'm going to use that as an anchor to see how well my model performs. There have been criticisms of this, so it's worth, if you think you want to explore this further, certainly look at some of the debates about using posterior predictive checks. Now, if we're comparing models, initially I'm going to use a Bayes factor. So remember, there's 3 priors. Now, the models that were best was a skewed distribution with random intercepts on all of the 3 priors. But now I can compare which prior is better, if you like, which supports the data better. And comparing initially the measurement constraint prior with the weakly informed prior, the measurement constraint prior, remember that was restricted to sort of values around, not restricted, but putting probability on values around plus or minus 2.5 meters per second, suggests that model is 18 times more likely under the measurement constraint prior compared to the weakly informed prior. So the measurement constrained prior came out as a better fit. Strong evidence, if you like, on a Bayes factor scale. Now the data for the measurement constrained prior compared to the informative prior, interestingly, is even stronger. So there's more evidence that actually the measurement constrained prior is a better model, if you like, of the data than the weakly informed prior. Sorry, than the informed prior, which is interesting in itself. Actually suggests that the data don't seem to reflect previous differences in other studies. Now, comparing models using leave one out cross-validation. So it's a different system of comparison. So I've just used Bayes factor, but now this is a different system. And there's, if you want to read the literature on this, you'll read literature on what we call open and closed models. So have a look at that if you want to look at which one you might want to choose. So LUIC, the lowest value is the best value, and in minus value, it's obviously the case in this case, minus 19.4 is lower than minus 11 or minus 6.1. So LUIC, sort of in that way, similar to AIC or ACI information criterion if you are used to comparing traditional models. So that seems the weakly informative prior, so it's a bit different than what we came out with the Bayes factor. Seems to be the best model. Now, comparing the expected log predictive densities, what I'm interested in here is not just the difference, but also how this difference compares to the standard error of the difference. Look, it's looking like the measurement constraint model is not quite as good on the leave one out cross-validation whereas it was with the Bayes factor. So there's some differences in terms of that. So these look like, anyway, the best models. Clearly, the informative prior didn't come out very well in either model comparison method. This first plot is a standard plot from the BRMS package, a conditional effects plot. On the y-axis, we've got sprint speed in meters per second. And on the x-axis, we've got measurement times. We've got 2 hours post and 24-hour post game. And we've got the groups, so we can clearly see treatment and control group. Now, what do those error bars represent? Well, the error bars represent not standard deviations, but they represent the credible interval. So they represent the 95% credible interval. Point is the most probable estimate for those particular groups. So we can see quite clearly the treatment group are on average faster than the control group in the 2 hours post-game measurement. And also in the 24 hours post-game, but the uncertainty, you can see the larger credible intervals, there's much more uncertainty associated with that, and they're clearly strongly overlapped. We can plot distributions, so have a look at that, and I'll plot those next, the pairwise comparisons. So here we've got a posterior distribution plot of the differences, the pairwise differences between each of the conditions and time points. The dotted line represents 0. This yellow distribution is our prior distribution, and these blue distributions are the posterior distribution of differences. So the peak is the most likely difference. Unfortunately, if we're doing this really, we might want to question some of these. Not particularly, it's not so bad on the questions we're asking, but some of these are not, they're multimodal points, so we might have some issues with that. But I'm not going to rerun the model. This is just for illustrative purposes. So what we've got here is at one of the points of difference, we want to know whether at the post measurement, do the control and treatment differ? There's a 100% chance the difference is less than 0. If we look at the second one where we've got 24-hour treatment and control comparison, well, there's more of an overlap. So it looked like there was on the conditional effects plot, and this plot suggests that as well. We calculate there's an 88.4% chance the difference is less than 0, which means that there's a positive effect because we're taking treatment away from control. So whereas it's clearly been effective above 0 2 hours after the game, it's more uncertain, as we saw on the initial plot 24 hours after the game. So as I mentioned previously, it's not just above zero that we can calculate the probability of. We can calculate the probability above any particular value. And we can know there'll be some measurement error. We might have a better idea, in fact, of what an important difference is. And to illustrate that, I've just gone with a 0.5 difference. So in this case, that 0.5 is standard deviation difference between the groups, I've set, if you like, as a region of practical equivalence. We might say that this is a region that's equivalent to zero, because above this is the values that I consider to be important. So I'm saying that this is equivalent to zero because of the measurement error, because of some value that I realise is actually important. I could choose any value. I've just chosen the standardised difference of 0.5, but I could go with a raw difference. You can calculate whatever you want to. So its difference is the probability above a medium effect. And so this is suggesting there's a 99% chance, or 99.6% chance of a difference, so that the treatment group's been better. When we go down 24 hours, what we've got here is a 68%, so almost 70% chance. So there is some evidence of a difference, but we can't really claim to be sure. We'd have to say that we really are unsure about how effective it is 24 hours after, but we're pretty sure that it's effective 2 hours after. So what can we suggest to practitioners? Well, quite simply, we can just use the actual direct probabilities, because they're actually quite reasonable to understand. So there's a 99.6% chance the intervention is successful in improving sprint speed after 2 hours than if you didn't do it. So the intervention's worth investing in if that's an important thing. So where you're in a tournament and 2 hours between games, this intervention is well worth using and investing time and resources into. A quote from John Tukey I think is really pertinent to Bayesian analysis. He said it's far better an approximate answer to the right question, which is often vague, than an exact answer to the wrong question, which can always be made precise. So I think with Bayesian analysis, you can focus on the things that you want to usually ask. That is, how effective has my intervention been? What's the probability that I've got an effect? What's the probability of an effect above a particular value? I think those questions can be really usefully addressed with Bayesian data analysis. So to review, prior scientific knowledge can be incorporated into Bayesian models very easily. That's possible with classical models, but much more difficult. In fact, this is the basis of Bayesian models. I hope you've seen that the results of Bayesian analysis are very intuitively interpreted. We can talk to practitioners and coaches and other researchers and readers of our research in ways that they usually intuitively understand in terms of probabilities that they use in everyday language. There is a 90% chance that this intervention works, for example. And complex models that are problematic for non-Bayesian analysis can be constructed and used. The last example was a series of different response distributions allowing for heteroscedasticity. So we modelled sigma across the different groups. It allowed random intercepts and in some cases random slopes, and we incorporated different degrees of prior knowledge. So a certain level of complexity. I hope this has encouraged you to have a look more into the possibility of Bayesian modelling in your own analysis, and that at least you've enjoyed looking at a different type of statistical analysis method.
Thank you ever so much again, Tony, for that. And thank you for jumping on a call again now for some follow-up Q&A after the pre-recorded lecture as well. Yes, I think the first thing I wanted to discuss really was what advice you've got for anybody wanting to start doing some of the things you talked about in your lecture.
Yeah, thanks, Stuart. Well, one of the things I'd say is the JASP package is really user-friendly. I mean, I know SPSS offer Bayesian sort of common tests now, but I think JASP is really sort of initially focused on that. and I think it's useful even where, I think one of the useful things you could do is even where you've conducted research before or using literature, there's actually one of the, I'll just find the name of it actually. It's one of the, where you can actually look at taking previous results and reanalyzing it. It's called the Summary Statistics Model in JASP. And I think that's a useful one for simple analysis like correlations and all, just to see, you can play with the priors. So you can look at the plots to see how that shifts with different prior assumptions. So I think that's one of the, perhaps a very easy way to get into it. If you've conducted research or are very familiar with research that's done fairly straightforward difference tests or relationship tests, you can use those direct statistics in that summary statistics module, and it will give you an idea of how different prior assumptions would shift. So, you know, it's essentially, you don't have to do any analysis at all, you put it in. I think that's a useful, gentle introduction. And then following that is actually just data you've collected, just to have a look at some of the basic tests, because they're sort of very similar. That it's user-friendly in the sense that they've got t-tests, paired t-tests, ANOVA, ANCOVA, regression. Now they've added mixed, generalized linear models, mixed models, and mixed effects model generally. So you've got, you know, it's growing, and it's University of Amsterdam, and they do constantly update things when a new program comes out. You know, a new update comes out. There's several different modules you can add to that. So I think that's a useful, easy way to get into it, because it's quite familiar for those who've used traditional statistics. There are also traditional statistics on there, so it's very easy to compare results, you know, with doing a, you know, if you do an independent t-test traditionally, then you can look at how different that might come out with different priors on a Bayesian t-test. I think it's probably an easy way in, really.
Okay, yeah, I think I'd second that as well. Having had a quick play around myself, I've not used the summary statistics module, but just I'm also a big fan of JASP. Like, I think it stands for Jeffrey's Amazing Statistics Package,
It does,
or
yeah.
something like that.
Harold Jeffries, I think that's acknowledgement.
Yeah. But yeah, it is, as you say, even if it's for frequentist or traditional statistics, it's very, very easy and user-friendly. And like you say, if you use the default settings, it is as easy as, instead of clicking independent t-test, you click Bayesian independent t-test,
yeah.
Or instead of clicking regression, you click Bayesian regression.
Yeah.
But I guess I was going to ask this question later on, but that's kind of led into it maybe. Something I've been thinking in my own research a bit, is JASP too easy, do you think? So with all the default settings for Bayesian analysis, is it too easy? So just a bit of a background there. My own journey really with this, I've initially started using some Bayesian research, but then I'm almost at the point now where I've realized I don't understand this well enough. And next time I use it, I want to do some more of what you did in the lecture of actually playing around with different priors. And I think potentially, yeah, it's very, very easy. Is that necessarily a good thing, or are there some negatives of that?
It depends what you want. I mean, the model types are limited. So you've got a Gaussian distribution, essentially a normal distribution for those models. It's limited as well to, say, in a difference test, to a standardized difference. So the priors are standardized differences. So when you can use informative priors, that's probably something that extend to other models. So at the moment, you can use informative priors on t-tests, for example, but it is on that standardized difference. So where you want to do something a bit different, where the distribution, and they're all symmetrical distributions, where you want to do something a little bit more challenging in terms of modeling, you might want to look at other programs. I think the benefit pedagogically of using something like STAN, even though it's a steep learning curve, is you really have to specify the model. So you specify priors on everything. I think a gentle introduction to that is the package I mentioned in the presentation, Paul Berkner's BRMS package, or RStanArm, which is the other STAN-linked package, which uses R code. So of course you've got to make this is only easy if you've used R, but the code's very similar to using other packages with frequentist statistics in R, so it translates very easily. You can also generate code from BRMS packages to have a look what the stand code might look like. It's not exactly like you'd write it in raw code, but you can see what priors are on what elements, because whilst you might in JASP choose just a prior for the standardized difference, really there are also priors on, if you're building a multi-level model, on the intercept, so what's the beta value, what's the standard deviation you're going to put a prior on. Now, the defaults produce, a useful place to start, because the defaults produce very similar models to frequentist statistics. That's what they're designed to do, really. So you could just interpret those as a Bayesian in a Bayesian way. But in essence, it gives you that, once you've got familiar with it, it gives that chance to be able to play with different priors. And it's very useful in terms of priors, really. I mean, it was a crude example that I gave in the presentation, just a limited example of saying, well, this is the difference. I didn't look at the intercept. I didn't, a standardized difference across all things, choosing just sort of a confidence interval from frequentist statistics and a measure of central tendency and mean difference. But you can do things much better in a way. You can do, where I showed an example of posterior predictive checks. You can do prior predictive checks. So in the code, you just put sample prior only, and it allows you to play about with how do priors influence results. Sometimes, in fact, the example I gave, it actually made them more conservative, because it's fixing it on a difference. So it made the differences a little bit less. You could say, well, even though that didn't come out as the best model, that may be the best choice, because maybe my data's, that data's more substantial. It was taken from a meta-analysis, or it was taken from a series of studies rather than my study. So it depends where you start. But that sort of, I think that flexibility and understanding comes from, having to run some model a little bit more complicated, probably gives you that idea of, what do these things actually do? What's the prize doing, and how do they influence results? And I think that can be useful. So I think JASP is a really excellent start. It's also gaining in terms of complexity, what you can do, and that, who knows where that'll end up. But to do things in a little bit more detail, and perhaps pedagogically to understand things, even if it's a bit of a steeper learning curve, something like using Stan or Python or some of the other, where you integrating with Stan, R or Python integrating with Stan, whichever you're comfortable with, depending on what background you've got, I guess. That's those packages like BRMS or RStan are useful introductions to that, I think. But and in terms of text on that, I think a very good pedagogical text in terms of Stan, even though I do like John Krushke's book on doing Bayesian data analysis. That was probably, I did a lecture with him in Oslo, and I think he was excellent. He was really good. Richard McElrath's book called Rethinking Statistics, they're both on, these are on second editions now, really starts very basic, building up models. So it's really interesting pedagogically to build up models. To start with, it uses his package, but it's in Stan, his extended code for a range of other sort of like Python, etc. So I think, that's a really useful introduction. Is it quick? Not necessarily. You have to work through it, work with it, but I think in terms of understanding, then it is really good.
Brilliant, thanks. Yeah, I think very good point you made early on in that answer was around, even if you use all of the default settings, you're essentially doing something very similar to what you would in a frequentist analysis anyway. And I think, from when I've played around with it, generally it's slightly or a slightly higher level of evidence. If you use something like a Bayes factor of 3 as your cutoff, generally you get very similar results, but just a slightly higher standard of evidence. So I guess, it is quite comparable. And another worry that maybe you can help put to bed is when you start, I think when people see you playing around with priors, they maybe start to think, is this getting a bit subjective? So rather than just saying, oh, I've ran a t-test, you're now saying it depends on the decisions I make around these priors. Can you maybe speak to that a little bit?
Yeah, I think, one of the things I think is useful is actually running different priors and seeing what effects it does have on your data. He said mostly there's certainly some of the analysis I've actually really done, which tend to make the differences, relationships more conservative than if I use the raw value. So it hasn't inflated things, it's done the opposite. It's sort of, and I've generally used priors really that have, what I might, and this is not a technical term, it's something I've used in the presentation called sort of measurement constrained priors. That's not a technical term really. What it is to say that I've looked at what the possibilities are in measurement. So I don't know, in the example I gave, I'm not an expert in sprint speed times or sprint, but I'd say that really, I think maybe the highest speed humans can get, you know, if I say that the biggest difference could be the highest sprint speed somebody could get, and say somebody fell over, that's the maximum they could be. So if I put probability over that, then I'm very safe in sort of not gonna, you know, I'm not skewing anything. Nobody's going to disagree that people could run, you know, 20 meters per second, you know, so, you know, I'm going to sort of constrain it within the measurement framework, and that tends to actually make things more conservative. You know, an extreme value is not going to necessarily pull estimates. So I think, to answer your question, really, I think I'd try out different priors. You have to obviously justify them. It's one of the things you need to do. Say, you know, if you don't know much about anything, a weekly informative prior and what that means exactly is useful. But try those things out. You know, in one paper, I definitely produced estimates of different priors because it shows, in fact, that actually the prior just made it more conservative, and a frequentist analysis would have been like a uniform prior, and it would have been a more extreme result than the actual Bayesian analysis with an informative or you know, measurement constrained prior. So I think don't be frightened of priors. You know, you're not trying to con people. I mean, I'm not saying that you can't with Bayesian analysis do like you can with frequentist analysis. Choose the data you want to do. You can still manipulate things if you're that, you know, of that mind. But of course, if most people are not, most people are honest and they want to present things and generally present evidence. So I think having a look at the effect of different priors is the best way of doing that, because sometimes it, you know, it might be that, you know, that you've got lots of data, priors get washed out. But where we in sports science often use quite small sample sizes, given the sort of way you test things, lots of, you know, lab testing, etc., can be quite intense, can be difficult to get really big data sets on that. So using prior information can be quite useful in that, but seeing how it affects your results, I think, is one way not to be frightened of that this is a subjective decision, that it's actually going to inflate things. I think often in practice it does the opposite.
Yeah, I think, again, the excellent point you made there was about justifying the priors. And it's the same as any decision you make in your statistical analysis, or I guess any of your methods. But if you're justifying why you've made each decision, people can follow that, but also it's there for reviewers or readers to evaluate. And I think, yeah, that's fine then. Yeah, and just the other point you mentioned was about some of your previous research, and just for the benefit of the people kind of watching this, some examples of papers where Tony's been involved and used Bayesian analysis. The links to those papers are below the video. So if you want to go and have a look at some examples, then they're down there as well. Yeah, I think probably the last slightly technical question I had was around, again, priors, but getting information for your priors from the literature. So can it be as simple as another study in a related area found this parameter estimate and confidence interval, or this mean and standard deviation, so I'm going to use those values as my prior? Or kind of, is there anything more complicated than that needs to be done?
It could be as simple as that, Stuart. I mean, it can be. It depends really on what model you're producing. So it can be as straightforward as that. But what I'd say is it's really worth doing those prior predictive checks to see whether that prior is reasonable, because in things we might not think have an impact can. So I think it could be just those, you know, just doing a straightforward, and then the example I gave was that really is a very basic sort of difference between groups, you know, control and treatment group previously. So it could be as simple as that, but I think that realistically you'd want to check that. You'd also want to check that against other priors, you know, so what you know, a default prior, what would be changing that prior slightly. Remember that, you know, we're trying to get that'd still be essentially often descriptive. You know, if it's a frequentist analysis, it'd be really their mean difference, for example, with a confidence interval on it. And we're trying to estimate, often trying to estimate, if you like, a population estimate or the data generating process or whatever you want to choose to phrase that. But so that may not be a good reflection of that in one single study. So it's, you know, it's still, you want to edge your bets a little bit and not make it too constrained, make it a little bit looser, but have a look. I think the thing is, simulating stuff where you can have a look at what the influence of particular things has on the analysis and the outcomes. As you see, if you have a look at JASP, you see that the example I gave was all of the priors made no difference in terms of the conclusions. So I think, you know, looking at that, where it does change your conclusion, that's where really that needs a bit more scrutiny. If it doesn't, well, you know, there's not really an issue particularly, but I think where it does change it, you know, it's often, that's where the problems may be if you're making a different claim than the rest of the priors. So what, you know, that's where you'd have to clearly justify the prior, clearly justify what you're doing. So it could be as simple as that, but I think you need to check and see what, against other things, and check, you know, in terms of prior predictive checks, etc.
Okay, so yeah, you mentioned about the possibility of it changing your conclusion, which is just another thing I was going to mention, just to be annoying, really. But you said at one point, I think in terms of frequentist statistics, you're not a fan of categories of effect size. So when we then, in terms of Bayes factors, when we then say kind of below 3 is anecdotal, 3 to 10 is moderate, and above 10 is kind of strong, very strong, extreme, etc. Like, is that the same thing? And are there any limitations of saying 2.9 isn't an effect, but 3.1 is, etc.?
Absolutely, Stuart. Yeah, of course it is. Yeah, anytime you put a category on a continuous variable, particularly when you get those things like 2.9 and 3, what's the difference? Very little, really. I mean, in terms of standardized differences, I'd rather interpret it in some way like Cohen's U3, or, you know, where you can actually be a percentage, or if people don't understand standard deviations, difference, for example. I think Bayes factor the same. It's how many times more likely. So I think in a way, you know, you can say, you know, you make a judgment and a claim based on that. So if something is 100 times more like, you know, the data are 100 times more likely under the research hypothesis than null, I don't think anybody would argue that your data, that's the case with your data and a reasonable conclusion. Where it's 2.9 or where it's 3.1, they're edges to a category and they're less certain, of course, you know. So yes, the hardbound categories are problematic, I think, always on continuous variables, and I'd caution against those. Particularly, I just think in a way it's like, I agree, you know, people want to know what does this effect size mean, and, you know, it's okay initially, I think, to have a look at those in sort of categories, but there is issues with them. And I think the same with Bayes factor. I think to introduce the idea of it, it's useful. To use as an absolute any mechanistic decision making tool, I'm pretty much against generally.
Okay. Yes. So I've got one more question before. Well, I think is this might be a yes or no, but with Bayesian analysis, do you need to correct for multiple comparisons like you would with frequentist?
You do if you're doing hypothesis tests. So I think in terms of, I think JASP offers some comparison. I'm not sure it does with Bayes factors actually. So yeah, in a way you can do that. I think if you're doing Bayes factor, it's a hypothesis test. You won't need to if you're doing parameter estimates necessarily, because you're not doing the same thing. You're trying to get the best estimate of a difference. So where you're trying to make a decision for or against the null hypothesis, then in a similar way you can. I think JASP, I don't really do that much hypothesis testing, to be honest, but I think if you look on JASP, there is some controlling for multiple comparisons, but you'd have to check really.
Okay. And then, yeah, I think the last thing I was going to mention, you probably covered most of it, because I know when we spoke before, I said about giving more information to readers or reviewers so that they can confidently evaluate a paper that's used Bayesian analysis. even if they're not used to doing it themselves. I think you've probably discussed a lot of things that would be useful there, and especially things like justifying all of the decisions and the priors. But is there anything else briefly kind of that you can think of to add that would help people to decide whether they're reading something that's done Bayesian analysis the right way or the wrong way?
I think the assumptions generally, so if you're using a linear model and you'd use a sort of likelihood, the assumptions don't change. They just replace basically, the random variables, but essentially if you're making a claim of, so there's similar assumptions, the same frequentist assumptions, you might get what error distribution you have around, so if you're doing a regression, for example, you might say your errors on the regression to get the confidence intervals are Gaussian, Gaussian error distribute, the errors are distributing in a Gaussian manner. You can do that the same on a Bayesian analysis. It's, you use a distribution, but it's a Gaussian distribution. I think it's easier to put different distributions in and check. So you could do skew normal. You can also have a look what a T distribution, response distribution looks like. How do those? But essentially, model checking in a way is the same. So if you're making claims of this is a linear model, then still those assumptions hold. So you don't suddenly magic away some of those things, those claims. So you still have to justify those claims, of independence or whatever else you're doing. So multi-level models or whatever type of model, the same similar assumptions in terms of the model hold still. You might still do some additional things about, as I say, posterior predictive checks, etc., prior predictive checks. Obviously, your induction approach is different, but in terms of the likelihood, that's the same as it is for a frequentist analysis. So so if they're trying to pull the wool over reviewers' eyes in a way and saying, I don't need this. The other thing is, I guess, where they say it's okay for small samples, it is, but it's not if you use a very, very weak prior. It doesn't really, it's still not that much better than a frequentist analysis. So on the whole, can it be useful for small samples? It can if you're using some reasonable prior information, because what you're doing is using that and then adding your data to it. Whereas if you've got a very few subjects and you're not using that, you're using a very weak prior, uniform prior, it's really not that different than doing a similar thing with a frequentist analysis. So it's not magic. If you've done bad data collection, then you're going to get bad results.
Excellent. Yeah, completely agree. And I think, that last point's really useful because you do hear within sports science, especially, a lot of people with issues around magnitude-based inference and things, but saying, oh, okay, now I'm going to use Bayesian analysis for small samples. And that's a very good point, that the benefits are around the prior, whereas if you don't really have any prior information, then you've still just got kind of a very small sample and you're not adding any extra information into that because there is no informative prior.
Yeah.
Okay, excellent. Well, yeah, thank you ever so much, Tony. It's been really useful, and thanks for joining for the extra chat now as well.
No, thank you, Stu.
Thank you. And just, for everyone else, I know we've had it on the screen, but just keep an eye out for the last couple of lectures over the next 2 weeks with Kristen Sanani, who gave an excellent lecture on statistics, but she's now back by popular demand and doing a talk with some tips for scientific writing, which is something else that she delivers online courses around. And then I'm really excited for Walter Herzog's lecture on muscle mechanics as well to finish it off. Yeah, thanks, Tony. Thank you very much.
Thank you. Cheers.